Well, good morning, pre-calculus. Take a look today at this pigeon. What the heck? So this is my classroom. A number of years ago, is a pigeon hanging out up on the ventilation ducts in the ceiling of the room. It had been flying around in the hallways. I keep my classroom door open. I didn't know the bird was out there. I mean, it was just a pigeon in the hall. Anyway, it flew in the door and then it wouldn't go back out the door. We tried to get it to go out the window, but my windows only they like crank open sideways. It only would open a little bit. Couldn't get the pigeon out. Um, Man, it was like flying around like it was a vicious pigeon, like attacking students and like pecking at their eyes and like yanking their hair out and like pooping on everyone. We were like running around like crazy. Students diving out the windows and like screaming down the hallways out of the towards the office like help us, killer pigeon, killer pigeon. Finally, one of the para eds came. Josh Carden came and helped, and he raises chickens, and so he's like, no problem. So anyway, we got it wrapped up in a towel or an old T-shirt or something, and we caught it and took it out outside and let it go, and it flew away. And was a better pigeon for the experience, having learned some math that day. And the rest of us were terrified. Um, actually, what happened was the pigeon calmly flew around. Well, the pigeon was not calm; it was freaking out, but it did not attack anybody. It wasn't pecking eyes or pulling hair. It didn't poop on anyone. That part I made up. More fun that way. Hey, so how did a pigeon get into my classroom? Well, that is a good question, and I'm not at liberty to discuss it, but let's just say that some students went to jail as a result of it. That may or may not be true, but that is my story. So, moving on from pigeons, today we're going to look at adding vectors, and so we got two learning targets for the day. First, we're going to be able to add vectors in component form, and secondly, we're going to multiply vectors by a scalar. Um, so here is the warm-up problem, which we'd be doing if we were in class. You'd be doing this on paper. It involves graphing, and so I went ahead and pre-drew the graph because I mean, you don't have any good way of probably copying this onto graph paper. So here's the story. From his house, a confused student, here's my student, confused student travels 4 blocks east and then 3 blocks north, 1 block west, 5 blocks south. At this point, he realizes he's lost and confused, stops and realizes, hey, I left my pet pigeon at home, whistles, and the pigeon flies straight from his house to the confused student. Okay, direction number one, already have done, sketch the path of the confused student. I also drew in the pigeon and then give the component form and the magnitude of the vector from home to the confused student as the crow flies. That is a good pun. Oh my gosh, it's too early in the morning for puns. Okay, so I'll assume that you've done this on your own while I was laughing at myself. So the pigeon is going to go 3 blocks to the right, so that's going to be +3, and 2 blocks down, so that's going to be a -2. So there's my component form in pointy brackets 3, comma -2, and the magnitude. Use the double brackets just to avoid any possible confusion to represent magnitude. So I got 3 squared plus -2 squared, and it's 9 plus 4. That's going to be 13. So radical 13, I'm going to leave it in radical form because that's the way we do it. Awesome. So we're going to come back and revisit this in a little bit, but let's move on for the time being. You remember, speaking of things that happened in the past, you remember the staircase from the escalator problem? We basically found the component form of the staircase, right? We found the horizontal length of the whole entire staircase was 477 inches. The vertical height to the elevation change of the staircase is 227 inches. We could write that into component form, right? Because we basically found the x component and the y component. We didn't describe it in those words, but basically that's what we did, right? Let's play pretend. What if there were two staircases stacked end to end? And instead of just going up the one staircase, he was going to go up both staircases. And we needed to find out what was the total distance that he went on the double staircase, right? Well, if I was going to add together to find the total horizontal length of the staircase. So let's start with this 477 inches. That's the horizontal measurement of the bottom staircase. And then we need to add that. And the number that comes next, obviously, is this 227. No, wait, you can't add those together. This one is a horizontal measurement, and that's a vertical measurement. They don't have anything to do with one another. I would add this 477 with this 477. So the total horizontal length is going to be 954 inches. And it's supposed to be purple. Let's see if we can make it purple. Purple. All right. And then if I was going to find the total elevation change of both staircases, I take this 227, that's the vertical measurement, added to this 227, that's also a vertical measurement. Those are going to add together to 454 inches. And so essentially what we've done here is we took the horizontal measurement, 477, we doubled it, right, to get 954. And we took the 227, that's the vertical measurement, or the y component, and we doubled it to get 454. So that's such a good looking 4. All right. If we think about it, if we have two staircases, wouldn't that be kind of like just taking our component form of the single staircase here and like multiplying it by 2? The answer is yes. It's exactly like that. So it's like kind of like distribution, right? We're going to take this 2 and we're going to multiply it by the x component. That'll tell us the new x component. And we're going to take that 2, we're going to multiply it by the y component, and that'll give us our new y component. And that is like, if we said it in different words, this is like one staircase. If we double it, that'd be kind of like putting a scale factor on it, right? It's a scale factor of 2. We got 2 staircases now. Right. Well, as it turns out, that's actually called a scalar. And the word scalar we can think of as basically meaning like a scale factor. So in order to multiply a vector times a scalar, it's just what we just saw. Our textbook makes it look super confusing and scary. So k is this is going to be a number. That's our scalar. So I'm going to like double it, multiply it by 2, or whatever number we're going to multiply by. This bold u, that's the vector, and so it would be a vector that's in component form. Okay, so that's the same. Multiplying a scalar times a vector is the same thing as you could write it with component form. So here's the scalar k, and the x component, it's called u1. The y component is called u2. We're just going to take this k and multiply it onto both the x component and the y component, and that's what this is showing us over here. Okay, so same thing we just saw with the staircase if we double the staircase. Right, here's the second example. If I have a different vector, this vector u has the components 4, 2. To find the component form, I'm going to change these directions. We don't need to find magnitude right now. So we're going to find the component form of 5u. Means I would just take 5 and multiply it by these components, 4, 2. All right, so we're going to multiply the 5 onto the 4. That's going to be 20. And I'm going to multiply the 5 onto the 2. That is going to be 10. 50 brackets and a comma. All right, simple enough. Cool. All right. Well, so maybe a couple of other examples. We could multiply by all kinds of different scalars. In this case, I've got 2 different vectors to keep track of. So I got a vector u is -1, 3. Vector v is 4, 7. If I'm going to multiply vector v times 2, that means I'm going to take, we'll color code, then we'll do this one in red. So I'm going to multiply 4 and 7. Both of those numbers get multiplied by 2. So this would be 8 and 14. Was going to do 3 times the vector u. Whoops, circling the wrong thing. Let's call u green. So multiply both the -1 by 3 and also this 3 times 3. So that's going to be -3 and 9. Negative numbers don't make any difference. We can multiply negative numbers. What if I was going to multiply vector u times -1? Oh man, that's actually not so bad. I'm going to take this -1 and multiply by -1 again. I can take this 3, multiply it by -1. So I'm going to end up with +1 and -3. And what if I took vector v and multiplied it by -3? All right, well, so that's going to be 4 times -3, 7 times -3. So I have -12, -21, doop, 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 brackets. Awesome. Okay. Um, let's think about this in a different way. If I was to go back up here, so multiplying by 2 on the staircase was a nice way of explaining vectors being multiplied by scalars. I could just say, look, I had 2 staircases. I need to multiply everything by 2. What if, just, I mean, think, I'm not going to redraw this, but think about it this way. What if these were not identical staircases? What if I had like a one staircase and then I added a second staircase to it, but it was a different sized staircase, right? Well, if the x components are different numbers, I can still combine them. You can still go up the first staircase and then go up the second staircase, and we can still calculate a total horizontal distance. It just wouldn't be doubling because they wouldn't be the same numbers, right? So we can, that's just addition. Right? I could take this x, add it to this x, it'll give me my new x component. I can take this y and add it to this y, and it'll give me my new y component, right? And that's exactly how vector addition works. Okay, our textbook, again, kind of makes it look scary, but if we have two vectors, vector u with a component form u1, u2, and vector v with components v1, v2, those are both vectors. It says let k be a real number scalar, but there's no scalar that shows up in the rest of this example, so we just ignore that for right now. The sum, which is called a resultant, when you add two vectors together, that's called a resultant vector. The sum of the vectors u plus v is, you just take the x components, let's color this x and this x, those get added together, that's going to be our new x components, and we're going to take this y component and this y component, and those get added together, that is our new y component. So if I have u is 2, 4, and v is 7, 3, then I can add the x's together and I can add the y's together. I like to do it this way. I like to stack them vertically so I can have this nice, just so I can work in columns. It makes it plus, makes it work neater for me. So I'm going to add the 2 plus the 7 together. That's going to be 9. And I'm going to add the 4 plus 3 together. That is 7. Why is that not blue? There we go. And whoa, no, come back. And since that is still a vector, I'm going to need my pointy brackets and a comma. Okay. Also just want to briefly touch so that's vector addition. The end. Also want to just touch on if we had a graph. If I was graphing this, I have vector u here. This is the 2, 4. I get this pre-drawn. So if I start from the origin and I go across by 2 and up by 4, there's my vector u. And then if I put vector v at the end of that, if I'm adding these two vectors together, it's kind of like what we saw with that student wandering around, right? I can do one move and then another move comes at the end of that, right? I don't go back to 0, 0 every time. So at the end of the blue vector, I'm going to start the green vector, which was 7, 3. So all together, this is like the confused student leaving home and wandering off in this direction and then turning and wandering off in a different direction, stopping, realizing that they're lost, and then they whistle and the pet pigeon flies from home right to the student, right, as the crow flies. The resultant is the pigeon, right? Let's make it red for resultant. And so we can see on the graph, as well as what we just got from adding the components together, 9, 7. And so that's what the pigeon has done. The pigeon has gone 9 spaces over, 7 spaces vertically, and it's represented on the graph as well as in the components. Okay, well, a couple more examples. So I got negative 1, sorry, find the component form, and we're going to skip the magnitude again. We don't need to do magnitude right now. Find the component form with the following vector addition. Yeah, vector addition, I should say that. So vector u is negative 1, 3. Vector v is 4, 7. All right, well, I am going to stack these up. So I got negative 1, 3. And you could do this in your head, but mental math is never good for examples. So I'm going to write it out. 4, 7. Add straight up and down these columns. So negative 1 plus 4 is going to be 3. And 3 plus 7 is 10. All right, here is my resultant. Super. So let's finish up with this. Let's go back to that story about the confused student and the pet pigeon. What if I redraw that same story, but in with a different drawing? So if the student does the exact same movement, 4 blocks east, 3 blocks north, 1 block west, and 5 blocks south, if I combine these two that are given in blue text, the 4 blocks east and 3 blocks north, to a diagonal movement, here's my student. So we'll just say, oh, it moves diagonally 4 blocks east, 3 blocks north. Blam. And then that'd be starting from the origin, draw the vector 4, 3. And then starting from the end of that blue vector where the student is standing right now we're going to draw this blue one, the 1 block west and 5 blocks south. We're going to call that one diagonal motion. So the student goes 1 block to the left and 5 blocks down, but in a diagonal motion. Oops, grab the student. Blam, student ends right here. Okay, so they end up in the same place. Whether we draw diagonal vectors or like we did in the original problem, we drew just the components, right? 4 blocks to the right was the x component, 3 blocks up is the y component, and the -1 is the x component of the next, and -5 was the x component of that next motion. So whether we work just in component form, we graph it as like um, orthogonal components, or whether we draw diagonal vectors makes absolutely no difference. We still end up with the same resultant, um, right? So here's, okay, so components or diagonal vectors doesn't make any difference as far as the end result, right? We're still going to get the same resultant every single time. Okay, so we already answered question number 5. Give the component form of the vector from home to the confused student as the crow flies. Okay, we said that was 3 and -2. I'm just going to bring that answer forward from last time. And then here's the last thing I want to look at. Here's our parting thought. What if the student wants to go home? Okay, there's a special name for that. If I can highlight it. So in vector, if we're adding vectors together, the net position change, it may not just apply to position, it could be like net velocity or whatever we're adding together, but the net change of 0 means all of these vectors need to add up to give us a resultant of 0. So if the student leaves home and wanders off in the blue direction and then turns and wanders off in the green direction and then wants to go home, so if we added like a third vector from the end of the green vector, what is that missing vector that would get the student home, right? Well, the secret is the pigeon knows, right? The pigeon knows how to get home. And so the pigeon says, hey, you know what? I just came from home. I can tell you how to get back there. We're going to do the exact opposite of what I just did to get to you, right? So if we've got a pigeon, we just need to reverse that pigeon. If I can flip that around here. So the pigeon is going to fly from is going to guide the student back home at the exact opposite direction. So the student will need to go -3 to get back home, -3 spaces or 3 spaces to the left, and +2 in the x direction, right? So if you know the resultant, like we found in question 5, to get a net position change of 0, it's going to be like the opposite of the resultant. So if there was no pigeon ever, it was just the student, then we could have the student wandering off in the blue direction, the student wandering off in the green direction, and then they say, oh, where's my house? Okay, I see my house. In order to get to the house, just ignore the pigeon this time. I need to go -3, +2. And then if we were to add together 4, 3, -1, -5, and -3, -2, all of those are going to add up to make 0. See if I can remember those. So we had 4, 3, -1, -5. And if I add together our answer to number 6 here, that -3, +2, when I add these all together, if I've done this correctly, it should give me, oops, a net of 0. So 4 minus 1, that'd be 3, and then -3, that's 0. If I add the y column, 3 minus 5 is -2, plus 2 is 0. Okay, so the net is 0. That is what the question is asked for. Give the component form of the vector that the student would have to walk to get home, or in other words, to have a net position change of 0. It's the same as the resultant, but with opposite signs on both the x component and the y component. That's how we get a net change of 0. Awesome. All right. Well, good luck finding your pigeon, and I hope that your pigeon brings you safely home. I'll see you again next time.